So today we're going to start Unit 7, chance experiments, sample spaces, events, right? The greater picture is probability. And so this will be a good review unit on what you should have learned, but most of you didn't learn. And so with that, we got to go through some definitions that we have. So you can see here, it starts with probability, we attempt to assign a value to how likely an event or an experiment is to occur. The value must be between 0 and 1, with 0 representing the probability that an event cannot occur and 1 representing a probability of an event guaranteed to occur. So I'm going to go ahead, I'm going to highlight pretty much those sentences because that really does highlight. Okay, so the value may be expressed in decimal or a fraction, and we can even do it as a percent. Usually in this chapter, we'll do it either as a fraction or as a decimal, okay? But I'll also keep throwing the percent out there just as a review. Capital letters are often used to represent different events. So there are two general approaches to calculating probability. The first is theoretical, which is based on reasoning, and then the other one is empirical, which is based on actual data. So you actually asked people in the room. You are likely only familiar with how to calculate theoretical probability, though empirical probability is utilized much more extensively in the real world. So let's review theoretical probability. So you can see here, theoretical probability is calculated by dividing the number of favorable outcomes by the number of possible outcomes. So you can see here, I'm going to box this and fill it. This is the formula basically for calculating. And you can see theoretical probability is P of X, P standing for probability, and it's a fraction. The numerator is the number of favorable outcomes, and then you divide that by the number of possible outcomes. Okay, so let's suppose we're rolling a 6-sided die, and we're going to do theoretical probability here. So we're not looking for actual data yet. So find the probability of each of the following. The probability of rolling an odd number. So the probability of rolling an odd number, let me just zoom in here a little bit. So I would write that like this, right? Probability, I'll just say rolling odd. I'll do it over 2 lines to save space. So, and then remember that it's favorable over total. Oh, well, wait a minute. What are the outcomes on a 6-sided die? So when you throw a die, what are the possible outcomes? So I roll a die. So are you guys all familiar with what a die looks like? Right? Okay. How many sides are on a 6-sided die? 6, thank you. Okay. And so we're looking for the outcomes. Aren't the outcomes just going to be 1 through 6? The sides are labeled, right, with 1 dot, 2 dots, 3 dots, 4 dots, 5 dots, and 6 dots. Do you recall? So of those outcomes, how many of them are going to be odd numbers? Yeah, we have 1, 3, and 5. So of the 6 outcomes, right, 3 of them are odd. So the favorable for this one is 3, right? Because the favorable is rolling an odd, so it's going to be odd number. And then the total is how many outcomes there are. And in this case, there's 6. So notice that reduces to be 1 and 2, right? Which as a decimal is 0.5. Okay, so if I were to represent it as a decimal, we would write it as the reduced decimal. If I write it as, I'm sorry, a fraction, we write it as a reduced fraction. If we write it as a decimal, okay, you can see that's what I have here. So, and then from junior high, you guys know that 0.5 is what percent? Yeah, remember, you're going to move the decimal place over 2 times, so that becomes 50%. Okay, the probability that it will land on a 2. So now this time we're looking for the probability of rolling a 2. So we're going to put favorable over total. So how many of the outcomes are a 2? So how many of these outcomes are a 2? Only one of them. How many total are there? 6. Okay. Now, if I take the calculator out and I divide 1 by 6, I'm going to round the number. Let's just go to 3 decimal places. This curriculum really likes going to 3, so we'll do 3. So you can see here, right, the reduced fraction is 1/6. The decimal approximation is 167 thousandths, right, or 0.167. What's that as a decimal? Yeah, what's that as a percent? Thank you. Thank you. Right, you move the decimal over 1, 2 times, and that's where it goes. Okay, probability that it will land on a 7. So that's just probability of a 7. How many outcomes favorable for that? Yeah, there's no 7s on a die, is there? 6-sided, they're labeled 1 through 6. How many total are there? 6. Notice 0 divided by 6 is 0. Okay, that's your fraction, that's your decimal. So that's 0%. So there is no chance of happening. There's no way to throw a 7 with one die that's 6-sided. All the conditions I keep throwing on there. Okay, and then finally, let's go to this last one, D. The probability it will land on 5 or 6, right? So recall that in math, the or allow for one option, the other, or both simultaneously. Obviously, if you're rolling one die, it's one or the other. So this is a 5 or a 6. So how many favorable outcomes are there for throwing a 5 or a 6? Good job, there is 2. There's still 6 outcomes. So we reduce that, that's 1/3. And if we stick that on a calculator, that will be 0.333, and I'm rounding, so I put that approximate there. So that's my reduced fraction. That is my decimal. And then you guys know that as percent, that would be 33.3%. But notice that I'm only highlighting the fraction and the decimal, and that's just because in this curriculum, they're going to focus more on representing the probability one of those two ways and not as the percent. Okay. I think we're so used to percents that I feel like we should put it up there. So, okay. So here's an exploration theoretical probability. So why don't we take a minute and do this together? It says in example 2, Alan is designing a probability game using spinners, right? So you would flick the arrow, right, and see where it stops. Okay. It will calculate his answer using theoretical probability. Since all sections are likely to occur, use probability notation to express each answer. Provide the answers in both reduced fraction and decimal rounded to the nearest thousandth. So they're basically asking for 3 decimal places there. Okay, so we're looking for the theoretical probability, and that's important because it's different from empirical. Okay, and they want you to write your answers both, right, as a reduced fraction, okay, and also as a decimal, right, rounded to the nearest thousand. Okay, so look at A. It says here, for spinner 1, calculate the probability of event A, which is spinning an odd number. Okay, now, I like writing it this way, so I'll say here, the probability of an odd number on spinner 1, right? So if I'm looking at spinner 1, there's 3 sections. How many of those 3 sections are odd? 2 of them. So it will be the 1 and the 3. So notice here, so the probability of an odd, the number of favorable is 2, right? Because there's 2 odd numbers. And total is 3. Can I reduce that fraction? Nope. If I put that on a calculator, 2 divided by 3 is 0 point, and then it's 6, 6, 6, 6, 6, right? Goes on forever. So we'll round it 6, 6, 7. Okay, and those are the 2 answers that they're looking for, right? So we have 2/3, we have 0.67. Understand that that is, right, 66.7%. And then something else to know, right? We can name our events. See how they call it event A here? You see that? So we could also call this the probability of A. For spinner 2, it says calculate the probability of event B. Event B is spinning an even number. Well, how many of those are even on spinner 2? Yep, 3 of them, right? We have the 2, we have the 4, and we have the 6, right? So the probability of an even, right? We have 3 possible, right? Favorable outcomes out of how many total? 6. Okay, well, I need to reduce that. That's going to be 1/2. And then what's 1/2 as a decimal? 0.5. And so you can see here that my reduced fraction is half. My decimal is 0.5. And the percent here would be 50%. Notice here, I could say the probability of B, because B is defined as spinning an odd number. Part C. For spinner 2, calculate the probability of getting greater than a 4. Oh. Probability, right? And I'll do this over 2 lines. Greater than 4. If it's greater than 4, does it include 4? No. So on spinner 2, how many of those numbers are greater than 4? Y'all agree it's 2? 5 and 6? Okay, actually, why don't we do this? I can do it in a different color. So right? 5, right? And 6. I did them in different. So there's 2 possible outcomes, right? Out of, or favorable outcomes out of how many total? 6. Okay, well that does reduce nicely to be, what is that, 1/3? If I put that on my calculator, that's 0.333, which is 33.3%. Okay, do you get the idea of doing just basic theoretical probability? Yeah? Okay, let's talk empirical probability then. Let's come down here. Says sometimes we have to quantify chance by using observations that have been made in the real world. In this case, we're talking about empirical probability or experimental probability. So this is going to be the big difference. This probability is going to be calculated based off of experiment, right? What we actually see. Once we gather data, we use a similar approach to quantify the probability. We divide the number of times the desired outcome is observed by the number of observations. And so you can see here, I have my basic formula right here. Empirical probability is equal to the number of desired outcomes, right, that occur, divided by the total number of observations that are made. Okay, so here we're going to come. It says here, the last banana. As we will frequently do in these units, we will be comparing our gut feeling, which we will call a guess, data from an experiment and with data from an experiment and theoretical probabilities. This situation involves a banana and some dice. Your teacher, I'm going to play a video is what I'm going to do for the class. So let's watch the video. We're only going to watch the first 2 minutes of the video. So let me come over here and switch locations. Okay, gotta stand next to this. Okay, here we go. Okay, that will be a good place to stop. Okay. So with that, now it says with, we're going to pair up, but let's not pair up. Let's just do it together as a class. And notice here, so we have two dice that we're throwing, right? Okay, and when we throw the die, if we have, if one of them is a 5 or a 6, then player 2 wins, right? But if it's anything else, right, where the highest number is a 4 or less, then player 1 wins. Are we clear on that? Okay, so notice here, it says, guess, would you rather be player 1 or player 2 in this game? So what do you guys, based on this, they said which player would be better? Player 2. So why player 2? That's what they said, right? So the higher, I'll just say higher theoretical chance of winning. Okay? This is by rolling a 5 or a 6. Okay, so we got our die. We're going to start rolling them. It says with your partner and 2 dice, you are going to play this game 30 times. So we're going to roll the dice 30 times. Each time you will record the largest number and then the winning player in the table below. When you are finished, you will calculate the number of times each player wins. Okay, so I handed the dice out. Okay, did you roll the dice for me for the first time? Tell me what the highest number is on the 2 dice. Okay, so the highest number when we rolled 2 dice was a 4. Who wins if it's a 4? Huh? Player 1. Remember, the highest die has to be a 5 or a 6 to be player 2. Okay. Will you roll it again? Ah, so if the highest is a 5, that means player 2 wins. Will you roll the dice again? I'm going to highlight the 2s just so I can see them. Ah, it was a 4 and a 4, so the highest is a 4. So that's player 1. Roll again. Okay, so 5. That's player 2. Roll again. 6. That's player 2. Remember, we're rolling 2 die here. He's just telling me the highest one of the 2. Okay, what's the next one? 2. That's player 1. Next one. That's player 2. Another 6. That's player 2. Next one. Oh, look at you. Okay, 6. That's player 2. Next one. 4. That's player 1. Next one. Player 2. Next one. 5. Okay, so 5 is player 2. Next one. Nice. It's player 2. Next one. That's player 1. Next one. That's player 2. Halfway done. Nice. Player 2. 4 is the highest. That's player 1. That's player 2. Another 6. That's player 2. 5. That's player 2. Oh my gosh. Player 1. 5. That's player 2. A 4. That's player 1. That's player 1. 5. That's player 2. That's player 2. That's player 1. That's player 1. 2 more. 6. That's player 2. And the last one. That's player 1. Okay, so looking at this chart, we know that we rolled the die 30 times, right? 30 times. So how many times did player 1 win? Well, let's count these out, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times. So that means player 2 ran 18 times. I see that in example 6. But it did ask for what's the probability of player 1 winning. Now, we're doing this time empirical, right? But it's really similar to theoretical. But empirical, we're just going to base it off what we actually have here. So we're going to have the number that were desired. And we're going to divide that by the total observed. So the number desired was the 12, and then the observed was 30. So as a reduced fraction, what 6 goes into both of those? Isn't that 2/5? Is that right? And if we put that on the calculator, it's going to be 0.4 as a decimal, or 40%. So there's my okay, and then for the second one, right, we're going to have the number of observed, or desired, sorry, divided by the number observed. So the desired outcomes here, well, we know it's going to be 18 because 30 minus 12, but And we have it here. We already counted them. So that'll be 18 over the total, which was 30. We do know 6 goes into both of them. This is 3, and this is 5. And if we put that on a calculator, we're going to get 0.6. So you can see that, right, that is our two outcomes. So, and then that is 60%. Were you guys surprised by the outcome, by the results? Okay, I have one student saying no. Were you expecting player 2 to win? Yeah, we were. Remember the video actually said that they had a chance. Did you expect it to be as big a difference, right? From 40 to 60, 40% for player 1, 60% for player 2? That's not too far off because I think they said 56%, right, for player 2. So I'm going to just go ahead. I'm going to write no. Just say the video said the theoretical probability was 56%, and 60 is close, right? Or 60% is close. Now, notice here, just to make a point, okay, I can't put this on the screen, but if you were to look at my notes, like when I did this, I actually got that 15 of the times player 1 won and 15 of the times player 2 won. So I had exactly 50%. So if you look at my answer here, I would say, well, yeah, I was actually surprised that it just broke up evenly, right? I would have expected that player 2 would have been higher, right? Not equal with. Okay, but empirical, this is how it can be. So it says here right below that oftentimes we will have to be content with using empirical as an estimate of the actual theoretical probability. In this case, we have enough information to calculate each player's theoretical probability of winning the game. Playing the game helps us to create a table to determine the sample space for this particular experiment. Recall that, again, you're supposed to have been taught that sample space, okay, of an experiment is a list of possible outcomes in the experiment. Okay, so the definition of sample space is a list of possible outcomes in the experiment. So you can see here on the next page, it says below lists the results of one of the die along with the columns. The table below lists the results of one die along the columns and the result of the other die as the rows. So your columns, right, are one die, and they're represented by throwing a green die. And then the second die, a red die, is the rows. Each cell represents a possibility of 2 die were rolled. Use the table to answer the questions below. So if I pick this one here, right, notice that it comes from the green die being a 3 and the red die being a 3. Now, of course, I picked the same one. Let's pick one that's not the same here, right? This comes from the green die being a 5 and the red die being a 3. Does that make sense? Okay, so how many outcomes are in this sample space? Well, we could count, right? But how many rows are there? 6. How many columns are there? So we could just do, if it's 6 rows by 6 columns, don't you just multiply those and it'll tell them how many outcomes? So therefore, there's a total of 36 outcomes. 36 total outcomes. Okay, then it says circle the outcomes which player one is winning. And then how many did you circle? So instead of circling, I'm going to highlight. And so notice here, for player one to win, right? The dice, nothing could be higher than a 4, right? So basically, if you notice here, it would be these 4 rows going along these 4 columns. Okay. How many did we circle or highlight? Yeah, 4 by 4, right, is 16. What is the theoretical probability of player one winning the game? Express the probability as a fraction and a decimal to the nearest thousandths, right? Well, the probability, right, of, I'll say here, player one wins. This is going to be favorable over total. So for player one winning, how many did we circle? 16. And how many are there total? Okay, so I need to reduce that. Looks like 4 goes into both of them. 16 divided by 4 is 4. 36 divided by 4 is 9. If I stick that on my calculator, 4 divided by 9, it's 0.44444, right, forever. But we usually just go to 3 decimal places, so 444, I'll round to the nearest thousandths. So that's my fraction, right? That's my decimal. Okay, and if I want that as a percent, it would be 44.4%. So how many outcomes result in player two winning, right? Well, we're going to have to go up and count those, right? So, and I could, right? I have, right, 2 times 6, that's 12 there, and then 13, 14, 15, 16, 17, 18, 19, 20, right? Or we could come down here, and wouldn't it be 36 minus the 16, right? There's 36 total. We know there's 16 for player one, so that means that there would be 20 here. So what's the theoretical probability of player two winning? So that's going to be the probability player two. This is theoretical, so I'll do favorable over total. So this time we know we have 20 over the total 36. Those actually both divide by 4, and we're left with 5/9 here, which as a decimal, right, is going to round, it's 0.55555 forever. So I'll do 556. So 5/9 or 0.556 as a decimal. Here's their 55.6. They said 56% because they rounded to the nearest whole, right? You see it? How do the theoretical probabilities compare to the empirical? Were the probabilities same, close, far off? And then why do you think they happened? And so for ours, we already basically said they were fairly close, weren't they? But did they have to be fairly close? No, they could have been way off, right? And so, what do you think impacts that? Like, how do we, if we really want to get a really good empirical probability, what do we have to do differently? Well, how about if we just did it one time? Damien, throw the dice. Tell me who wins. Okay, who won? Huh? So if we stop there, right? Our sample size is only one. There's a 100% chance player one wins, and a 0% chance player two wins. Does that match up with the theoretical probability? No, right? It should be like 56% player two wins. So do you think that the sample size matters? It does, right? Do you think 30 is a pretty good number? What if I did 100? Do you think it would be closer to the theoretical probability? Yeah, I would guess that it would be too. What if I did 1,000? Probably that much closer. Okay. So do you get the idea? So I would just say here it's fairly close, and why, I would just say, let's just put a note here. Because we did not have a large sample space, our empirical probabilities can look different from theoretical. Okay, I'll just write here. So because we did not a large sample space, our empirical probabilities can look very different. From the theoretical. Okay, are we okay with that? So you can see the next page, it just has the lesson summary there for sample space, event, theoretical probability, empirical probability. So you guys can take a chance to look that over. Your homework tonight is to do worksheet 7.01. And I think with that, we will wrap up the lesson.